Welcome viewers, to this tutorial on analog and mixed-signal IC design. In this lab session, we will walk through several important aspects of analog IC design using Cadence tools.
By the end of this session, you will have a clear understanding of the following points. First of all, I will tell you about the role of different Cadence software in the custom IC design flow, and the key tools involved. How to log into the Linux environment and launch Cadence Virtuoso. What is a process design kit or PDK, and how to manage different libraries using the library manager. Once the environment is set up, we will design the schematic of a CMOS inverter using the Virtuoso Schematic Editor and simulate the circuit using Analog Design Environment or ADE Explorer. After that we will analyze its waveforms in ViVA, which stands for Virtuoso Visualization and Analysis. Finally, I'll show you some frequently used shortcut keys in Cadence Virtuoso to improve your design productivity. I'll also attach a reference for these shortcuts at the end. This is the flowchart of custom IC design. First, the specifications are given, which define what the chip should do. Based on these specs, the schematic is created basically, which are the blueprints showing how the circuit will be designed. Next, the schematic is designed using Cadence Virtuoso, and simulations are run using Cadence Spectre software to check if the circuit behaves as expected. After verifying the schematic through simulations, the design moves to the layout stage, where the physical chip layout is drawn using the Cadence Layout Editor. Once the layout is complete, it is checked for errors with tools like Cadence PVS and Pegasus. These checks include DRC, or Design Rule Check, and LVS, or Layout versus Schematic, to ensure the layout follows all design rules and matches the schematic. If any errors are found during these checks, the layout is revised to fix them, and the checks are repeated until the design passes. After the layout passes these checks, post-layout simulations are performed. These simulations account for parasitic effects, small unwanted resistances and capacitances in the layout, that can cause a slight degradation in the circuit's performance compared to the schematic simulations. If the results do not match, revisions to the schematic or layout may be necessary. Once everything is verified, the design is converted to GDS2 format, which is the file format sent to the foundry for chip fabrication. After fabrication, the IC is tested using a measurement setup to ensure it meets the required specifications. This completes the custom IC design flow. Now, let's move to the software part. First, you will see my screen running Linux Red Hat. To get started, click on Activities, and then go to Files. Here, you can create a new folder or directory. For example, I have already created one with name user2. Open the folder, and make sure it contains the files cds.lib and cshrc. The cshrc file tells the system where your tools are installed, so you need to source it for launching any Cadence software. When you source the cshrc, it sets the correct paths for the Cadence tools. The cds.lib file contains information about different working libraries, like the PDK, Process Design Kit, and other analog libraries, which you need to include before starting your design. To do this, right-click anywhere in the folder and open a new terminal window. In the terminal, type CSH and press Enter to start the C shell. Then type source CSHRC and press Enter. You should see a welcome message for the Cadence tools, confirming that the environment is set up correctly. After that, to open any Cadence software, simply type its name in the terminal. For example, if you want to open Cadence Virtuoso, just type Virtuoso and press Enter. It is called the CIW, or Command Interpreter window. This is the main interface of the Cadence Virtuoso tool. From here, we manage our libraries and design projects. To begin, go to the Tools menu and select Library Manager. This opens the Library Manager window. You'll typically see it appear on the left side of your screen. In the Library Manager, you'll see a list of libraries. These include the ones defined in your cds.lib file. Some of the libraries might come from the Cadence, such as Analog Lib Library, Basic Library, AHDL Lib Library, and others. These libraries provide the components and models needed to create and simulate your schematics. If you want to create your own library, here's how you do it. Click on File, then select New and then click on Library. Now give your new library a meaningful name. For example, you could name it something like AMS_tutorial_1. After typing the name, click OK. Next, you'll be asked whether to attach it to an existing technology library. This step links your new library to the appropriate PDK. In this example, I'm using the 65 nanometers low-power PDK. If your technology library is listed, like GPDK45 or 65 nanometer low power, select it from the list and click OK. Now your new library appears in the Library Manager under the name you gave it, like AMS_tutorial_1. Now, let's create the schematic of a basic CMOS inverter. We will begin by using the AMS Tutorial 1 library we created earlier. Click on the library, then go to File, then New and click on Cell View. Make sure to set the type to Schematic. Now give your schematic a name. I will name this as Inverter. After typing the name, click OK. This opens the Schematic Editor window where we'll design the inverter using PMOS and NMOS transistors from the PDK. To place components, press the I key, which stands for Instance, or click on the instance icon. Then click on Browse. Navigate to the 65 nanometers PDK, and from the list, choose the PMOS transistor, typically labeled something like PCH_Mac. Select it, close the browser, and click anywhere in the schematic window to place it. Next, we'll add the NMOS transistor. Repeat the same process, press I, Browse, and select NCH_Mac from the PDK. Place it just below the PMOS. Now it's time to wire the components. For wiring, press W key on your keyboard. This enables wire mode. Click to start and end each wire segment. Once the transistors are wired, we need to label the connections. Press L key for labeling, and type in appropriate names like in, out, VDD, and VSS. These labels help us recognize different nodes in simulations. Let's now connect the bodies or bulk terminals of the transistors. For the PMOS, the body, or bulk, should be connected to the highest potential, which is VDD in this case. For the NMOS, the body should be connected to the lowest potential, that is VSS. You might recall from theory that PMOS transistors are usually made wider than NMOS transistor to balance their drive strength. In this tutorial, we will use a PMOS transistor that's twice the width of the NMOS transistor. So if our NMOS has a width of 400 nanometers, we will set the PMOS width to 800 nanometers. To do this, select the transistor, press Q, for Properties, and set the width accordingly. Press OK to apply. Next, let's add voltage sources to power the circuit. Press I, browse into Analog Lib Library, and search for VDC. Place it in the schematic. For VSS or ground, select the source, press Q, set the DC voltage to 0 volts, and name it as VSS. For VDD or supply, again press Q, set the voltage to 1 volts, and name it as VDD. These voltages are essential to ensure correct operation. Now, let's add a pulse voltage source to simulate the inverter input with a step signal. Browse again in Analog Lib Library and look for V-pulse. Place it and then wire it up. For a meaningful pulse, we will set the following values. At time 1, 0 milliseconds, and voltage level 1, 0 volts. Till time 2, 3 milliseconds, and voltage level 2, 0 volts. At time 3, 3.01 milliseconds, and voltage level 3, VDD volts. Till time 4, 6 milliseconds, and voltage level 4, VDD volts. At time 5, 6.01 milliseconds, and voltage level 5, 0 volts. Make sure you specify time units like milliseconds and voltage units like V. Missing units can lead to simulation errors. Once this is configured, press OK, finish the wiring, and label the input and output nodes if not done already. Now the schematic of the inverter is ready for simulation. Now, let's move over to the simulation side. First, click on the Launch and then ADE Explorer to open the simulator window. If the window is not already open, just create it by clicking Create New View. After that, it will ask to create a Maestro view of the cell. Click on OK. You'll see the Maestro interface. On the left side of the window, it has different steps you'll follow to simulate your design. To start, we need to choose the type of analysis. For this tutorial, I will select a transient analysis simulation. Double-click on the analysis option. It will then ask you for the simulation parameters. Set the simulation time, run it for 10 milliseconds, select the Accuracy Defaults to Conservative and then click OK. Next, you can import variables from your schematic. Simply right-click on Design Variables, and select Copy from Cell View. For example, if you want a parameter to be set to 1 for VDD, type 1 in the value field. In the simulation setup, you'll also see options for parameters and corners. For now, just uncheck these to keep it simple. Now, let's set up the output waveforms. For this, go to Outputs, then click on To be plotted, and then click on Select on Design. You can select the nodes or wires you want to plot by clicking on them and adding them to the output list. Press Escape key to exit selection mode. Before running the simulation, go to Setup and check your model libraries to ensure everything is correctly linked. If not, you can add it by going to PDK and select the proper model libraries and then select its section type. Once everything is set, click on Run the simulation. After the simulation finishes, open the waveform viewer. You can maximize the window for better visibility. You will see the input and the output waveform. To customize the plot setting, select a waveform, right-click on it, and choose Style, then click on Solid. You can also increase the line thickness for better visibility from Width option. Now, observe the waveforms. When the input is low or 0 volt, the output is high or 1 volt. When the input goes high or 1 volt, the output switches low or 0 volt. This confirms the inverter operation. It outputs the opposite logic level of the input. You can also add differential markers to the plot to measure voltages differences. Press M for placing single marker on any waveform point to get exact values. For differential markers, which measure voltage differences between 2 points, select 2 points by pressing A and then B. This is useful to analyze signal behavior between nodes. Now, I want to tell you about some useful hotkeys in Cadence Virtuoso. These hotkeys will make your work much faster, especially when working in schematics and layout. For example, press W to draw wires. Press I to place an instance, like a transistor or any other component. Press P to put pins on your schematic. Press L to label any wire or net. Press Q to view or edit the properties of an object. These are the most common shortcuts you will use while designing schematics. I will attach a full list of these shortcuts with the video for your reference. Besides these, there are some other commands that are used less often but are still handy. For example, when we get to the layout part of the lab, you will use the ruler tool to measure distances, accessed via the K shortcut key. And again, I to place instances during layout 2. To undo an action, simply press U. To redo, press Shift plus U. These undo and redo shortcuts are lifesavers when you want to quickly fix mistakes. This was all that we have covered in this lab. In the next session, we will discuss the DC voltage characteristics of a transistor. We will study the basic behavior and then perform simulations to analyze these characteristics. This will give you a solid understanding of transistor operation in circuits. Thank you for watching. We appreciate your time and hope you found this tutorial helpful. See you in the next session.